All right. So we talked about isomers, chirality yesterday. Today we're going to talk about enzymes and what isomers actually have to do with the real world here, how this actually works. One of the cool things, we're going to practice drawing some isomer structures today, and we're going to do the molecular model activity and get into the lab and play for a little bit. So as you continue with your notes here, you should be on this page here with the enzyme, the active site, the substrate. This is a bit of a biology application, so let's read here. Many substances in living organisms, such as amino acids, which make up proteins, have chirality, okay? So many substances have chirality. And here's the interesting part, only one chiral form is used because it is the only form that fits the active site of an enzyme, okay? So here is a diagram of what we're trying to explain here. So if this is an enzyme and this is a substrate, so again, I'm not a biology teacher, you can learn this in biology, but enzymes speed up processes, are important keys to biological processes. Without enzymes, the big thing is a lot of times these chemical processes would take thousands of years, and guess what? We don't have thousands of years between breaths. We don't have thousands of years for us to live, okay? So enzymes are part of speeding up, making efficient the keys to a lot of these biological processes. And so if we have an enzyme here, it's got a specially shaped site, you can think about it that way, and the substrate fits in like a lock and a key. And so in order for these processes to happen, the enzyme and the substrate have to fit together, and there's only one chiral form that would fit in the site. Okay, I should mention here before we get too far into the video, because I think you can see me here, it's mismatch day. This is why I'm dressed like this, mismatch day, okay? This is not a regular outfit. Okay, as we continue. Optical isomers have the same physical and chemical properties except in chemical reactions where chirality is important. So we talked about this yesterday. The chiral forms, the left and right-handed versions of certain molecules, have much the same properties, just like my hands have much the same properties. They can do a lot of the same things. They look very much the same. They behave the same. But there are specific things that my right hand can do that my left hand can't, and so on. And so a lot of the same properties, but there are some very unique and amazing chemical properties that only one chiral form will be able to perform. Okay, so let's get some practice drawing. This is from our last lesson yesterday. So structural isomers, remember structural isomers are how they are connected, the structure, right? If you're building a house, okay, does the house have a roof like this? Does it have a flat roof? It's the different structure, okay, how they're connected. So this should be in your notes. Do you have a blank here in this spot for your notes, right? Okay. Now this big black mess is covering the answer. So I want you to draw all of the structural isomers that are possible for the alkane. Remember, that's a singly bonded. Alkane has single sigma bonds only, with the molecular formula C6H14. You only need to show the carbon chains. You do not have to draw all of the hydrogens. Okay, don't have to draw all the hydrogens. Just show the carbon chains. Okay, so single bonds, how many different ways can you draw different structural isomers? I'm going to give you a few minutes to do that. And obviously, you might want to check out a straight chain. Does that work? Does that have a formula or not? You want to check that out? Okay, so go ahead and go, and I want to give you a few minutes to see how you do with this one. Okay, so here are the answers. The structures are over here. Sorry, I did all that. The video was paused. So there are the structures. Okay, straight chain. You pull off a carbon, put it onto the third carbon here, and it looks like this one. Take a carbon from the end, jump it over, and put it onto this carbon. There you get your third one. And you can take the end carbon, put it on the middle carbon, and then take another end carbon and put it on the same carbon. These are the 5 different isomers, and here are their names right here. We're going to talk more about these names coming up. This looks really difficult and really strange, like 2,3-dimethylbutane. You're like, oh my goodness. But don't worry, we'll take it just a step at a time, piece by piece, and we will learn how to name these, okay? That's structural isomers. All right, next page. Let's see. The next practice that we have here are these. Draw the stereoisomers of cis-3-hexane and trans-3-hexene. Oh, hene and ene. So there's a few things going on here. There's cis and trans. We talked about that last lesson. There's the number 3. So you got to go back to your notes. Remember what we did yesterday. What does the 3 mean? What does hex mean? And what does the ENE at the end mean? So all of this information is important. Go ahead and draw the 2 stereoisomers of cis 3-hexene and trans 3-hexene. Go ahead. Okay, so let's reveal the answer. Here it is. Now, there's 2 different versions of the way you can write. This is kind of a condensed structural version. This would be more of a 3D version. I would encourage you to draw these ones, okay, because they're a little easier to see, but this is also just a way that you might see it in a textbook. Okay, so let's go over this carefully. Cis means same side, right? Yep.
What if you didn't draw the hydrogens?
You have to draw the hydrogens in this case. You have to draw these hydrogens to show what's going on here, that these hydrogens are facing opposite ways. They're just as important as the carbon chains. So you don't have to draw the hydrogens on all of them, but you would have to draw the hydrogens here just to like they did here. Okay? Yeah. Good question. All right. So again, cis means same side. So that means the chains or the hydrogens will be emanating sort of from the same side, the same direction, from the carbon of the double bond. And remember, this double bond here does not twist, right? It doesn't twist. I'm just gonna move this over. It cannot rotate around this way, okay? It's rigid, just like the fingers here. So the cis would be like this, right? Or like this. They cannot twist fully. They can only rotate fully. They just twist a little bit. And then the trans means opposite side, okay? So that's why we have the chain on this kind of chain emanating on the opposite sides. Same sides here, opposite sides. That's cis and trans. The 3 references the bond position of the double bond here, the ene, the double bond. So it's the 1, 2, 1, 2. So here's, let me read. First bond position, second bond position, third bond position, okay? Counted from either side, So it's the third bond position, that's where the double bond is. And then of course the hex, right? The hex refers to how many total carbons in the chain. So in this chain there are 1, 2, 3, 4, 5, 6 carbons. Yeah, question?
How do you know, like,
Okay, yeah, good. We talked about that yesterday. But that is the number of hydrogens. So in here, we're not drawing the hydrogens here on this formula except for the ones that are pertaining to the cis-trans part. But and it's tough to see maybe here at the back there. So the reason why there's 3 is because on this carbon right here, there are actually 1, 2, 3 hydrogens that are bonded, and then this is the 4th bond for carbon. Here, for this carbon is bonded singly to this carbon and bonded singly to the carbon up on the right there. And so there's only room for 2 more bonds, so there's only 2 more hydrogens that are onto this one. Okay, so that's why this is a 3, this is a 2. This would technically be just CH1, because we've got 1 bond here, 2 bonds here, that's 3, and then a 4th for the H. Okay?
What?
The ene is the double bond. Remember, ane is single bond, ene is double bond, ein with a Y is the triple bond. Yep. Hex is 6 carbons, correct.
How would we know how many hydrogens?
Okay, how many hydrogens go for each carbon? Remember, each carbon can only have a maximum of 4 bonds, and it does want 4 bonds. Yeah. So if one of these bonds is going to another carbon, such as the case with this first one right here, 1 is going to the carbon, there are 3 bonds left for hydrogens. For this carbon right here, okay, 2 bonds are going to this carbon, 1 bond is going to this carbon, so there's only 1 bond position left. That's why there's only 1 H on this carbon right here. Okay? Any other questions? Good, that's some important stuff we got figured out there. Okay, cis and trans, very, very good. Okay, let's do, I think, one more here. And then, yeah, just one more for this exercise. So this one should also be on your notes. If you have your notes in front of you, you should have a space there. this is where we practice drawing an optical isomer. This might be the toughest one, I'm not really sure, but starting with a single carbon atom, okay? So a single carbon atom like this. Draw two different optical isomers by attaching the following atoms or groups to that carbon. So I want you to attach a hydrogen, that would be kind of like X from yesterday's lesson, a CH3, or this is a methyl group, that's like the, sorry, this would be like the W, let's say, W, X, the methyl group. This is an ethyl group, so this is like the Y, and then propyl group here, which you don't know those names yet, but that would be like the Z. So attach these four in two different ways, just like we did yesterday when we talked about optical isomers. So you're going to have one over here, and you're going to have a second grouping over here. Go ahead and take a minute to do that. Look back to your notes if you're trying to remember how to arrange those optical isomers. All right, here we go. Here's what your optical isomers might look like. Now, let me just outline the differences that you need to show here, okay? Now, you might think, and those do not look different at all. I don't get that, but let's break it down. Remember what we said. If we have, W, X, Y, and Z in this order from, top going around whatever, clockwise, okay? If we have that, if that is one of the ways that we draw one of the isomers, then what we have to do is we have to make sure that this group right here that is opposite of H has to be next to H now in our new diagram. Or, think about it this way. One of these two that are next to H here, you see, this one is next to H and this one's next to H. One of those have to not be next to H now. They have to be opposite. So here we go. I did it this way. X, straight across, and then Y, and then Z. Okay? So that's how you show, so W, X, Y, Z. That's how you show the optical isomers. One goes around in a circle, in a wheel, and the other one goes across the carbon, and then across the carbon a second time. So if you were to see this in 3D space, they would not all be in the exact same relation to each other. Okay? That's the way you draw optical isomers. Okay? You have again, yours might be, you might have started with H over here, or you might have done things a little bit differently, right? The key is, as I mentioned, you have to start with, let's say, start with your H here, that's what I labeled as W, and then Y, X, Y, Z has to be kind of in order around the circle. Then that order has to change. So so if this was W, X cannot be one of these two beside. X has to be straight across the carbon in your diagram. So it has to follow this pattern. It doesn't have to look just like this. It has to follow this pattern that I explained. Does that help? Okay. Now, if you want me to take a look at what you drew later, just to confirm, I'd be happy to do that. Okay. Awesome. Okay, anybody else have any questions about this? All right. So that's what I wanted to accomplish today. Just finish our talking about about chirality, how it's used. It's some practice on drawing isomers. So that's this little lesson today. We are now going to move to this molecular model activity, which is right here. So yeah, if you lose this paper that I'm giving you today, or if you want to print this off yourself at home, you can find that, of course, on mrmathwold.com and look up your Chemistry 30. You can just download it and print it off, and there you have it. The molecular model kits, we are going to move to the lab here right now and take the last half of the class to get started on this activity. So that brings this to a conclusion.